Here is Gabriel, who is going to talk about robust Bell inequalities from communication complexity.
Hola. What? Ah. Can you hear me? Yes. Well, thank you, Glaucia, and thanks the organizer for inviting me. Um, so, in a nutshell, the result I want to tell you about is a way to construct unbounded quantum Bayes violations from gaps in communication complexity. Now, for those who don't know some of the words in this short summary, don't worry, I will explain later. But for those who do know, let me tell you some salient features of the construction. The violations that we get can be exponential in the size of the inputs or linear in the number of inputs while having a constant number of outputs. And the construction applies to every quantum classical gap proven so far in the literature. And they are robust to white noise and detector inefficiency. Okay, so I will start with a short introduction to communication complexity. In the typical scenario, we have two players, Alice and Bob. Ali gets an input X, Bob gets an input Y, and they want to compute a function f of y by communicating messages in a distributed fashion. And so we wonder the minimal amount of message they need to communicate, in the worst case of the inputs, to compute f of xy. Now, there are several measures depending on the type of messages you have and on the class of protocols you allow the players to execute. The simplest case is a deterministic protocol and communicating bits. And well, it's very easy to see that the simplest strategy, Alice just sent her input to Bob, and Bob computes f of xy. So as an upper bound, we have the length of the inputs. But there are some functions for which this is the best strategy. For example, computing the equality between two strings. Then we can move to a model where we allow the players to have shared randomness. Usually, when we consider random protocols, we go for a model of bounded error. So we allow the players to make an error in an epsilon fraction of the inputs. And of course, a random protocol, a deterministic protocol, is a particular instance of a probabilistic protocol that uses no randomness. So this is an upper bound. And already for this model, we have infinite separations. For example, for the equality, with a constant number of bits, there is a random protocol that computes with bounded probability of error the equality function. But there are functions for which, again, the best strategy is sending the whole input. For example, the disjointness function, which asks, given two strings, where there is a position where both have 1, given 2-bit strings. Now, if we move to the quantum model, there were two models introduced. One is where the players communicate qubits, and the other one is where they communicate bits but they share entanglement. It is not hard to see that the communicating qubit is an upper bound to communicating bits and shared entanglement, because you can transform every protocol that communicates qubits into one that communicates bits and shared entanglement using teleportation. And you have these two factors there. And we have separations between quantum and classical. For example, for the disjointed function, we can do with the square root of n. And we also have exponential separations. For those who know, this is Rust problem, or also known as vector in subspace. But this is a promise problem. This means that we only expect the players to output correctly in a proper subset of the Cartesian product of their inputs. And I guess what the biggest question in this area is whether there is a total function for which there is an exponential separation between quantum and classical communication complexity. So in the paper, we work with a more general model of communication complexity in which we don't consider functions, but we consider the simulation of probability distributions. And so here, the task is we want Alice and Bob to output according to some probability distribution P. And the error model we consider is distance in trace distance. Okay, so we wonder how many bits or qubits they need to communicate in order to output according to a distribution P prime, which is an epsilon trace distance from the target distribution P. And okay, here again you have the same relationship between classical and quantum. Quantum is at most as big as classical. Well, it's easy to see that you can recover the scenario of computing functions by studying the communication complexity of simulating this distribution. But I'm not gonna go into detail with this. Okay, now some definition from Bell non-locality, which we've seen during the day, so it will be quick. Probability distribution, we say it's local when there is a classical protocol, which are randomness, which communicates 0 bits and outputs according to this probability distribution. Well, this forms a polytope, so an equivalent definition of being local is being inside this polytope, or non-local, the existence of a Bell inequality that separates this point from the set of local distributions, and since this set is a polytope, there are only finitely many Bell inequalities to check. And well, a quantum distribution is where the players, again, share entanglement, don't communicate, and output according to P. A quantum strategy for a distribution. This means that a distribution is quantum whether there is a strategy of this sort. Well, this is what I mean. So what I just said, you can give the definitions of local distribution and quantum distribution in the language of classical and quantum protocols. So this relationship between the scenarios of communication complexity and non-locality led people to wonder whether these are two sides of the same coin, as some author put it. And in our work, we studied, so you can study both relationship, whether for every Bell violation, you can construct a communication complexity problem for which there is a quantum advantage, or you can study whether for every quantum advantage in communication complexity, you can build distributions and Bell inequalities for which you have a validation. We studied this last direction. And so first, let me define, because this is not too widely used concept, what I mean by unbounded violation. This means that I have a family of Bell inequalities and quantum distributions, say indexed by n, such that for every m, there is one of these Bell inequalities and one of these distributions for which the violations distribution achieved on this Bell inequality is greater than m. Okay, this is what I mean by unbounded violations. So the first general result in this, going from a quantum communication complexity advantage to a Bell violation, was given by Berman and co-authors in 2016, and says that for every function, there is a Bell function and a quantum distribution for which the Bell violation that distribution achieves on this Bell inequality is lower bounded by the ratio between the square root of the classical communication complexity of the function and the quantum communication complexity of the function. Now this general construction has, before that, let me rewrite it in this way, this equivalent way, just to tell you that I will call Bell functionals which are bounded in absolute value on local distributions, I will call them normalized Bell functions. Okay, so this construction has some pros and cons. In the pros, the inequalities that we get are meaningful in the sense that we can interpret the coefficients as given the success probability in a game. Also, a positive quality of this construction is that it's inherently resistant, the violations that you get, resistance to local adversarial noise. On the cons, and this is what we try to improve in our work, the distribution that you get have an exponential number of outputs, exponential in the length of the inputs, and a doubly exponential dimension required in the quantum states given rise to this distribution. Also, like you see, in order to have unbounded violations, you need that the gap between classical communication complexity and quantum is greater than quadratic. And there are functions in the literature for which we have separations between quantum and classical, which are less than quadratic. And also, this more technical, this construction doesn't work for protocols which, on top of communicating qubits, share entanglement. Well, the violation of normalized Bain inequalities, the maximal quantum violation of normalized Bain inequalities has been studied, and we have upper and close to matching lower bounds. For example, as just I'm going to mention the upper bounds, n, the number of inputs, and well, a constant, yes. What do you mean by coefficients? No. It can be negative coefficients, but the value on local distributions had to be upper and lower bounded by 1 or by a constant, but we had to be both upper and lower bounded on local distributions. And so we have an upper bound of n, of number of outputs, and yes, linear also in the dimension. I think I'm going to skip this, but the maximal quantum violation of normalized inequalities can be related to the resistance of noise of these quantum distributions. And now to present the result, I'm going to go to the scenario of the detection loophole. So here you allow the players to abort their protocols. This comes from the scenario of the detection loophole when in some of the rounds of the experiment you may not get conclusive outcomes. And so it may be the case that if you condition the outcomes to only those non-abort outcomes, it may be the case that you observe that you end up with a non-local distribution when, if you had looked at all the outcomes, including the aborting outcomes, the distribution was local. So, for example, you can win the CHSH game by just letting Alice abort half of the time. So there is a strategy in which Alice abort half of the time, and if you condition the resulting distribution to the non-abort outcomes, you get a pair box. And so given a distribution, you may ask the largest probability of non-aborting for which there is a local protocol simulating the distribution. This linear program here, whose maximal value we call efficiency. And well, if you look at the dual, you get Bain inequalities. I'm going to call the Bain inequalities, which are solutions to the dual of this linear program, inefficiency resistant Bain inequalities. These are Bain inequalities which are only bounded above, but on a larger set. So on the set of local distributions, we may abort. And it was already observed by Mazar in 2002 that the log of the optimal value of this linear program is a lower bound on classical communication complexity. What is more, it's one of the strongest bounds that we know on randomized communication complexity, on classical communication complexity. These are the many techniques that we have, and you see that. Okay, so it's equivalent to the partition bound, which is a bound that was studied in communication complexity, and it turns out to be equivalent to the efficiency bound. And it's, like I said, one of the strongest. So moving to the results. So the first one says that for every distribution for which we have a lower bound on the log of the efficiency, in other words, a lower bound on the log of the partition bound, and we say a lower bound of C, and we have an upper bound on its quantum communication complexity. Say we have a protocol that communicates Q qubits for this distribution. Then we can construct a Bell functional, which will be an efficiency-resistant Bell functional, and a quantum distribution such that it gives a violation of this order, so exponential in the difference between the communication complexities. And it's bounded above on local distribution that may abort. And the proof is relatively simple. So if we have a lower bound on the efficiency, then we know that the solution to the linear program is lower bounded by 2 to the C, say the lower bound was C. And this is witnessed by the solution to the linear program, which is a inequality. Now, if we have a Q-qubit protocol for a distribution P prime, which is an epsilon trace distance of P, we can use teleportation to transform it to a 2Q bits entanglement-assisted protocol for this same distribution P prime. So what I'm trying to do here is go from a quantum protocol that may communicate qubits to a quantum distribution. So first, I'm transforming the quantum communication to a classical, and now I'm going to remove the classical in order to have a distribution. And how I do this? Well, the players will pick at random a string of length 2q, the size of the classical communication. If the teleportation measurements match the shared string, then they continue with the protocol as is. Otherwise, they will output a new symbol. Let's call it A. Okay? Now, this is a randomized communication complexity protocol with zero communication. This means that the simulated distribution, a quantum communication complexity protocol with zero communication and shared entanglement. This means that the resultant distribution is quantum. And this is the resulting distribution. With probability 1/2 to the 2q, the protocol doesn't abort and outputs according to P prime. P prime, remember, was a distribution an epsilon distance from the target distribution. Otherwise, it just outputs some new symbol A. Now, what is the value of the Bell functional that we get from the linear program on this quantum distribution? Well, since B does not have coefficients on this new output A, the value it takes over this L distribution that for which for every xi, at least one of A or B are A, with probability greater than 0, is 0. So the value of P over Q is just by linearity, 1/2 to the 2Q, the value that it took that it takes on P prime. But since the value that it takes on P prime, we know from the lower bound on the classical combination complexity as T2DC, then we get this amount of violation. Is this clear?
Okay. Would it be a tight quantum bound on this strategy that you generate is the best quantum strategy for this game?
So in what sense?
Because you create a non-local game that with this quantum strategy that achieves at least that bound, or that achieves this bound.
Yes, but optimal in this in what sense? Because
if there is if there can be another quantum strategy that makes better.
That has a larger violation on B. We don't know. Yes. So it may be the case there are quantum distributions that for these solutions of the linear problem that we get achieves a higher violation, and I will talk about upper bounds on the violations that we can get in a minute. Well, this is just a comparison with the previous construction that I told you. So what the important things is that we have a constant number of outputs. It really doesn't matter the amount of the violation because these are different Bain inequalities, but I guess the more important point is that we get unbounded violation for constant number of outputs, and that our construction applies to functions studied in the literature for which the gap between classical and quantum communication complexity is smaller than quadratic. Okay, so the violations that we get from theorem 1 are, the second result is that they are resistant to white noise. So if instead of the ideal quantum state psi, you have rho, then the magnitude of the violation is the same if and only if the noise is less than the difference between the error bounds in the lower bound on classical communication complexity and the protocol for the quantum communication complexity. Okay, but remember that I told you that at least in Burman construction, we knew explicitly the coefficients of the Bell inequalities, and what's more, we cannot. There is meaning in these coefficients. Well, but in our construction, this is just a solution to a linear program. Well, for a particular for a subset of the lower bounds on the efficiency that we have, so there's a lower bound technique which is strictly smaller than the partition bound, but for which we know separations in classical and quantum communication complexity. Whenever the separation between classical and quantum communication complexity is proven with this less powerful technique, we get analytical expressions for the Bell inequalities. This is the case, for example, of the disjointness function, that I told you before. And well, the last result is that you can transform every inefficiency resistant Bell inequality into one which is now also bounded above in local distributions that may abort, and the magnitude of the violation is only affected by a constant on non-signaling distributions. Okay, let me finish with some future directions and open questions. This is the one that I like the most. So remember I told you that people have studied upper bounds on the maximal quantum violation that you can achieve on normalized Bell inequalities. We asked the same question for this new family of Bell inequalities, which we call inefficiency resistant. We know that this is upper bounded by the number of inputs, just because this is a lower bound on randomized communication complexity, and this is upper bounded by the size of the inputs. we've proven that it's not bounded by the number of outputs, because we have unbounded violations with constant number of outputs. But we don't know whether there is a bound as a function of if we can get unbounded violations with fixed dimension. And why this is important? Well, because a positive answer, meaning a construction of unbounded Bayes violations of inefficiency-resistant Bayes inequalities with constant dimension, would imply that we need, since this is a lower bound on classical communication complexity, that we need infinite communication to reproduce all the correlations of bipartite entangled states of this dimension. This is I forgot to put the references, but this is what we know so far. So for two outputs at dimension 2, we know that with 1 bit of communication, we can simulate every quantum distribution with these parameters. For 2 outcomes and dimension D, we can simulate all correlations with 2 bits. But already for 3 numbers of outcomes and dimension 3, we don't know. Okay, well, then it would be nice to find experimentally relevant violations with this construction. The ones that we have are not, because because of the hidden constant in the lower bounds and the upper bounds to the classical and quantum communication complexity. And last, there is still open whether there is a function for which the classical communication complexity is larger than the square of the quantum communication complexity, but for which the efficiency bound is equal to the communication complexity, to the quantum communication complexity. And this would mean that Boltzmann construction apply and ours not. This is still open. Well, that's it. Thank you very much.
Thank you. Questions?